Unit 2, Day 2. We talked about this last class with the definition of the derivative, and we did a lot of algebra over this, and we were able to find what this f prime of x equation equaled after the limit was plugged in and what it represented. We will finalize today what it represents. There is an alternative form, okay? Now here's the thing that I'll tell you. On the test, we will tell you to do specific ways, and this is for Unit 2 test. I will say using alternative form of the definition of the derivative, find the derivative of this function. Okay? And then I will say use the definition of the derivative. We must know both, but if it doesn't say which one to use, I would say 9 out of 10 times, this one's going to be the more easier one, and at the same time the more useful one. Because this is a function that might look like, I don't know, let's say it simplifies out to 2x squared. And what the derivative function means is this. At any given point in time, it will give you a velocity of a particle in motion. Okay? So let's say 3 seconds. I want to know how fast something is traveling in 3 seconds. Let x equal time. So if I put 3 right here for x, we know that it's going to be 3 squared is 9, times 2 is 18. So let's say 18 feet per second. So this is just an example problem. At 3 seconds, we have 18 feet per second. That's the velocity of this particle. Okay? If I were to take the derivative of this, we're not going to do it the long way right now. I'll do it the shortcut way. I would get the second derivative, which in this case is 4x. Now, conceptually, I want you to know what this is doing before we start doing all the algebra. So f double prime of 3 is going to be plugged in here, and I would get 12 feet per second squared. And then last but not least, let's say we had this. Okay? And this could be like 2/3 x over 3. And if this is my f of x, I have f of x is 2/3 x to the third. And if I wanted to know at 3 seconds, well, I would get 3 cubed is 27 divided by 3 is 9 times 2 is still 18 feet. Now this is what we're doing. If you've seen the movie Inception, or whether you haven't, I want you to start thinking about these 3 dimensions, if you will, of position, because it's just f of x, of velocity, and of acceleration that are going to be used with these derivatives. If I said, what is the rate of change of something? Right now you would probably say the rise over run of that something. But we want to develop that a lot higher because it's not just the rise over the run, it's the change in its value over the change in time. So if it's 2 positions and I did the rise over run or change in those positions over a change in time, I would get the velocity. So the rate of change of position goes to velocity. The rate of change of velocity goes to acceleration. So you remember in that movie, there were levels of dreams? Like f of x was reality, if you will. And one level, or your first level of dream, was f prime. And whatever happened on that level did affect your reality back on f of x. Because they're all related. They're all connected. So at an instant in the cosmos of time, at 3 seconds, I could know what is something's position, what is something's velocity, and what is something's acceleration, all at the same instant in time. So imagine this. Imagine that someone is diving off a high dive. And as they're diving off and they're falling toward the water, you take a picture. A picture is worth 1,000 words, because in this respect, that picture alone, if you were to go and just show like a calculus class this picture, and you were to say, what's happening in this picture? Position-wise, that person's at 18 feet. You see what I'm saying? Velocity-wise, that person, this would actually be a negative 18 for that example, but they're falling to the ground at negative 18 feet per second. Even though you're not watching video, you're not looking at a video, you're looking at an instant in time. But at that instant, they're moving negative 18 feet per second. And the last thing is, how fast are they accelerating at that instant in time? So derivatives are rates of change between things. Okay? Now, we solved it last time the long way. Okay? This one is a little bit shorter, but this gives the equation for all values. This one is just for one value. So all slopes can be solved from this one, where this one it's just one slope. And now you probably see, why would we ever even use this if we're just going to find the velocity at one instant in time? You with me? But no both. So what I want to do is I want to go to the example that we used last time, this one right here, and we're going to do the second, the alternative form for this. Okay, here we go. First of all, our answer, and you could go back and see from that video that I'm going to fix with audio, came out to 2x minus 4. Okay? And if I wanted to know what would it be explicitly or exactly at f prime of 3, you tell me from what you've been hearing, what would the answer be here? What's f prime at 3? 2. Okay? So this is basically the slope at x equals 3. The slope is equal to 2. AKA f prime of 3 is 2. You with me? Okay. So now, don't let this second alternative form confuse you. It is going to look or feel a little bit different, but nonetheless, we're still going to get the same answer. Okay? All right. It's the limit as x approaches c of f of x minus f of c. This is the derivative of what? What goes here in this parentheses? C. This is the derivative at 1x value. The other one that we did, it wasn't f prime of c, it was f prime of what? Of everything, f prime of x. So guys, the definition of the derivative, I want to make sure that you see it. It's an equation that'll give you all all velocities or derivatives. Bless you. So I have limit of h approaching 0, h is on bottom, f of x plus h minus f of x. Now let me highlight these as I go. Still y2 over y1, minus y1, and this is still y2 minus y1. The only difference is the answer is an awesome equation that you can plug any number into. But the answer over here is if and only if we're evaluating one specific x value, which doesn't make sense, but we need to know how to do it as well. Okay. Notice the similarities and differences. The setup on this, if you remember, and I'm just going to set them up, was x plus h squared minus 4x plus h. This was y2. Okay? Which is, let me color coordinate it. Whoops. Right here. Okay? And then we subtracted y1. So subtracting y1, aka f of x, we get the original equation here. It's all over h as h was approaching 0. you help me out over here? What's this approaching? C, which in this case is going to be what? 3. And here we go. I need an f of x. What do I write there for f of x? The equation. X squared minus 4x. Now we're going to do minus f of c. What do you think I write for f of c? Plug in the 3. So let's write it out like this. F of 3. Okay? All over x minus 3. Are you with me? Okay, here we go. Let's solve for f of 3. That means we're going to take a 3 and we're going to put it right here and right here. You tell me, guys, what would f of 3 equal if I plugged it in? Negative what? Negative 3. So this is going to now change to a negative 3. Are we still good? Okay. The top over here will simplify to x squared minus 4x plus 3, and it's all over x minus 3. What should we do? It's not approaching infinity, so I know we're kind of doing this because we postponed our test, but these aren't infinite limits. What should we do?
Wait, question, what was the negative 3 before you changed it?
F. Are you talking about what was this?
Yeah, what was that before you changed it?
F of c. So in other words, we took this value of input of 3 and we plugged it into this equation and we got 9 minus 12 to get negative 3. So when I subtracted negative 3, it's adding 3. And yes, someone said it. What do I do? Factor it. So I'm going to factor the top. X minus 3, x minus 1. And you see the piece that would otherwise make this undefined. What are we going to do with that piece? We're going to cancel it so that the limit as x approaches 3 is left with that. Now, if I plugged in 3, guys, what would I get? 2. This answer is the derivative, aka f prime, the velocity or the rate of change, the derivative at 3 is 2. That's exactly what we got here when we did it the long way. Okay? Yes? See, this right here, notice the difference in the answer. Here, I only got one number. There's no variable. It's not variegated. There's not a variable there that it's waiting for an input and it'll give you any output value of the derivative. But this one is. That's what makes this one awesome. Because I can put any number in there and I'll get the derivative just like that. If I put 0, the derivative is negative 4. If I put 10, the derivative is 16. You see what I'm saying? Alright, so the last bit that we're going to do on this is that we're going to write the equation of the tangent line. Okay? So this is just a position, x1, y1, and a slope. AKA now we're in calculus, so we're going to say, what is the slope at 3? We said it was 2. Okay? So the slope at 3 is 2. You with me? What would the position be at 3? What did we say? Negative 3. Now, we have to know what level of these dreams of inception or reality that we're plugging this 3 into. If I plug 3 into the position function, which is here, I would get negative 3. And from Algebra 2 and Algebra 1, we were used to seeing this as this point right here. This right here, we got the slope is 2. In Algebra 2 and Algebra 1, we were used to seeing this as m is equal to 2. So the point slope formula is the most important equation that you'll use in regards to tangents in that respect. So it'll be y minus negative 3 is equal to the slope of 2 times x minus 3 And there's your answer that you could even write it like this if you want. Or you could simplify it to y equals mx plus b. So you have 2x minus 6, subtract the 3 over, 2x minus 3. This is the equation of the tangent line, and so is this. So this and this are both equations of the tangent line. Okay? And the tangent line is this. Wherever my graph is at, the tangent is going to touch that graph only at one point. Okay? And we'll get to that here in just a bit on the next couple of slides. Questions so far?
Shouldn't it be y equals 2x minus 9?
Oh, minus 9. Yes, thank you for catching it. I will add points to your team. Any other questions?
Is this on the test on Tuesday?
No, this is not, because this is Unit 2. Okay. Let's move on to... Come on. Alright, here we go. We're going to look at derivatives, quick derivatives, and their graphs, okay? For instance, let's go to... Let's go here, and then I'll go back to those graphs so that you can see them conceptually. The derivative and differentiability. So a function f is said to be differentiable. It's able to be differentiated. I'm able to take its derivative, aka it's able to be rate of changed at x is equal to c if the derivative of x exists at x is equal to c. In order for the derivative to exist, the graph must have local linearity. Okay? So in other words, if you zoom in over and over at x is equal to c on the graph will look like a line, but not a vertical line. Okay? So a function f is not differentiable if it has a sharp turn. Okay? So here we go. I know it's a little early, but it is true what I'm about to say. What Caleb was asking earlier is, what does a derivative really even mean? A derivative is this. It's an equation that can help you predict the future. It can help you predict the future of something that you're calculating how it's changing. What's the rate of change of stocks? What's the rate of change of profits? What's the rate of change of costs? What's the rate of change of a tumor that might be benign or that might be malignant? Different rates of change so that we can predict what is it going to need to take to fix or predict what we're doing, what we're working with. Okay? Some very, very powerful stuff. Okay, so sharp turns. Let's say that this was your life, per se, and it was monitoring... wait, what? Debt? That'd be cool. Debt, let's say that it was...
Just right back up.
Oh, okay, no worries. Okay, so let's say that this was someone who was trying to lose weight per se. This was their weight, and it's going down at a linear rate. So they're losing rate as time goes on, and then all of a sudden it just shoots straight up. My question to you is, because it was so sharp of a turn, did you ever see this coming? No, you couldn't predict that it was actually going to change drastically. But nonetheless, it did change. So right here, we're going to say f is not differentiable. It's not able to be seen the future as far as projected at 2 because it's such a sharp turn at x is equal to 2. So f is differentiable for all other values. For instance, this word for right now, guys, I want you to put it synonymous with slope. What's the slope, everyone? What's the slope right here? -1. What's the slope right here? +1. But what's the slope at a corner? Who knows? We can't tell. It does not have local linearity. slow curving and slow changing that we can predict its future. Okay? Here we go. The next one is 2. F has a discontinuity at x is equal to c. So, right here at c is equal to 2, you can see that there is a discontinuity. What kind of discontinuity is it? Infinite discontinuity. Is it removable or non-removable? Non-removable. Can we predict the future where something doesn't exist? No, we can't. Here, the point existed. Let me help you out in the correlation of what you're going to be tested on next Tuesday. Here, f of c is defined. Continuity, first rule. You with me? Here, f of c is not defined. So we can't predict its future. We can't take the derivative at c. Yeah.
If there's a removable discontinuity, can you take the derivative?
Nope. Okay. Let's go to a vertical tangent. Can someone tell me what's the slope of that vertical line? It's not 0. It's undefined. Because what's the delta x of this line? Well, let's say that there's a point here at 0, 1. And there's another point here at 0, negative 1. And I did way back when y1 minus y2 over x1 minus x2. Can I do this? No, it's undefined. Undefined, right? So this one, you also cannot take a tangent. And last but not least, this cusp. So sometimes at corners, they're not necessarily straight corners per se, but nonetheless, it's a graph that comes together that still feels like a corner. It's a drastic rate of change. Okay? So that would be your final one that you cannot take the derivative of. Okay. So now, let's use the alternative form of the derivative, and we're going to do this example first. Okay, here we go. I'm trying to find what is the rate of change at 2 on this function right here. So the alternative form that you will have to build, and the work that you're going to have to show for Unit 2 is this. Approaches what? 2. Approaches 2. Okay? It's going to be over x minus 2. Because already you see, you just created this undefined moment from the alternative form of that equation for the derivative. Now, it's something, y2 minus y1. Drew, what's the first equation that I put up here? X minus 2 to the 2/3. Guys, please, so that everyone is consistent, please, 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 and you'll understand later. Any number, I want you to have a horizontal line. Don't do diagonal fractions. Please don't, okay? Don't. Because a lot of times, we don't realize that we're wrong sometimes with the way we write them. So please, for the sake of consistency and speed for grading especially, please write those horizontally. Feet per second, yeah, we could write those diagonally all day. And that's what I want you to do. Units are diagonal, but numbers are horizontal. All right, Lexi, what do I write here? It's this minus what in the numerator? Not x plus 2, but... So remember the equation? It was f of x minus f of c. So what's our c value, anyone? 2. So we're looking for what is f of 2. So that means I'm going to plug this 2 right here. And what do I get anyway? I get 0. Okay? So this will be x minus 2, 2/3 over x minus 2. And we're approaching. You with me? Alright, so what could I do from here, guys? I have, say again? I have the f of x minus the f of c. And my goal is to find some way to cancel this x plus 2 or get it out of its denominator in some sense. Actually,
So would it just be 1 to the 2/3 power?
let me let you work on it in groups just for a little bit because I want you to talk about that power and how it simplifies. All right, so let's go 2 minutes. All right, don't lose points for talking, please. Here we go. Here's the equation. We built the equation for the alternative form, which is f of x minus f of c over x minus c. We get to here. We know this is all to the power of 1, otherwise 3 over 3, however you want to look at this. And we know powers, if they're subtracting, it's going to be 2/3 minus 3/3, which gives you a negative 1/3. We know that this is the same as if you were just to write it like this, which some of you did. Some of your groups actually showed this as far as being downstairs to a positive, or you could have drawn it like this nonetheless. So you're taking the limit. Oh, my bad. 1/3. Thank you. So the cube root. So now, if I'm approaching 2, this is the most simplified form. We use the equation. We try to cancel out the denominator, but unfortunately the denominator did not cancel out. And this right here, if I put 2 in, I don't get 0. I would get undefined. So undefined. No one got that? No worries. Undefined. We should have got the answer. All right.
I thought we weren't supposed to get.
2 minutes.
I thought we weren't supposed to get.
Back to the video. X approaching C. X approaching C on this is 1. And I'm looking for f of x minus f of c. Guys, what did y'all write for f of x here? 3x. And what is the c value, or f of c? 3. Because you plugged in 1 for x and you got 3. And then it's x minus what here on the bottom? 1. GCF tells us we would have this. We canceled out the piece that otherwise would make it undefined. And this should be the answer. Now, what I want you to do starting now is I'm going to give you a little bit more time, but I want you to show this on your board when you submit it. And please, when time is up, you have to submit it. Not still writing. Please pay attention and make sure that you are looking at the time.
So you're just saying the limit as exponent, not all the work.
Yeah, no, not all the work.
Right.
You would just do what's in blue right here. Okay? All right.
Cover up the whole whiteboard.
Let's go now. Let's do these two together. All right, here we go. First of all, let me get some points. All right, here we go. List the x values for which, we're going to do this together, for which the function appears to be not continuous. Evelyn, what x values do you see? 6. What else? That's it, right? That's it. That's correct. So x is equal to 6 is the only one. Differentiability. Let's go, Luke. What values do you see that are not differentiable? Luke. John, let's go. 3. All right, so 3 is one of them. So we'll say x is equal to 3, and why is that not differentiable?
Because it's at a point. It makes a hard turn.
Okay, so cusp. Okay, let's go back to Luke. What's another x value, Luke, that it's non-differentiable? 8. For the same reason. Let's go to Caitlin. What's another x value that you see that's not differentiable? 4. Nice. Because of? vertical tangent. Yep, vertical tangent. And Matthew, what's the last one? So 5, and you could say because of what? A cusp? Are there any other values that you guys see that it's not differentiable? 6. And this is because of a jump discontinuity. Okay? Alright. So we know for it to be differentiable, it must be continuous. It must be continuous to be differentiable. Okay? It must be continuous. And at the same time, it cannot be a vertical tangent, and it also cannot be a cusp. Okay? So, let's come over here. And actually, I'm going to show you just real quick on this graph what tangents can look like. So, I want to do a tangent here, 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 let's say here. So let's have a volunteer. Who wants to volunteer and come up? Nice, 100 points. So I want you to draw a tangent line at that first x value. That's awesome. That's perfect. It's a tangent line that hits the graph only at one point at this x value right there. You with me? Now, let me have another volunteer that draws a tangent at the second one. Come on up. Just push back arrow. Perfect. Next one, volunteer for the third one. Come on up. I'm giving points to those who are volunteering. The ones who volunteer first get more. Okay. So now let's think about tangents, guys. The steepness of these lines is the tangent. You with me? So this one, if I were to ask you, what does the slope kind of look like? What would you say? What steepness would you give that? 1. Looks like a y equals x, right? What's the steepness? And a lot of us go to that 45-degree angle of 1. What would you kind of give, let's say, Saeed, what would you give the second one? A negative what? So like a negative number. Give me a negative number. What's the strength of that steepness? I'd say it's like maybe kind of higher, right? Like maybe 5 or 10. So maybe like a negative 10. I know, they're just big approximations, okay? And then this one, like a positive 10, right? Maybe a positive 8, somewhere around there. Now, what if I wanted to know this one right here? What's the slope there? 0. Nice. So it's 0 because it hits at a horizontal line. You with me? How about right here? It's like a vertical tangent. It's like right here, a tangent would look like a vertical line. So like Caitlin was saying from before, it would be a vertical tangent. It's non-differentiable. Okay? Alright, so with all that, let's come back to this. And we want to know at which labeled points is the slope m 0. Yes?
Can a tangent not cross the graph then?
Okay, so this is a good question. If I have a graph and I have a line that looks like this, technically, how many points did this line cross the graph technically? 3, right? Okay? the line goes forever.
Yeah,
My
yeah,
point
yeah,
is,
yeah.
if I have a graph that looks like this, and I have this line, how many points did it cross? 2. So we call this, you've seen this with trig, but conceptually with graphs, a line that crosses a graph at 2 points is called a secant slope. A secant slope, if you don't know it already, is what you've been doing since day 1 of Algebra 1 pretty much. Okay? y2 minus y1 over x2 minus x1 is a secant slope. A tangent slope will only touch the graph at how many points? Just 1. Okay? So here's the thing. If I wanted, and it's just practice with the graph, if I wanted to know when the slope is 0, what letters up here could you say the slope would be 0? B. There's a horizontal tangent because the slope of that is 0. E. When is it positive? That's C. And D. You with me? So the slope is 0 at x equals B and E. The slope is positive at x is equal to C and D. And finally, it's negative where? At F. Okay? Does anyone see any relation or extension, kind of what we just did, that they want to add to this? Just curious if you kind of see a correlation.
I just have a question.
Yep.
So, if you drew a tangent slope at D, say, wouldn't it go through the graph at, like, between A and D?
Okay, good. So here, oops. Dylan's absolutely right. As far as the way it goes through the graph later, you kind of think maybe that's a secant slope. You with me? But what it's talking about, local linearity, means in the vicinity, in the immediate vicinity, surroundings, it's only touching at 1. Are you all good with that? Do you understand? Local linearity is just looking at a small little smidget picture of the surrounding areas. Yes?
So what makes it local exactly? Like what if it's, zoomed out a lot? Like how do you know?
So here's the thing. These are big questions, and they're awesome questions. And I keep adding just points to awesome questions in that respect. How do we know if it's not zoomed out or zoomed in? Here's the thing with local linearity. A tangent will hit at 1 point, no matter what. And only 1 point. Whereas, no matter how you zoom in or out, I see what you're saying. The secant is conceptually just looking at 2 points, no matter what. And again, can we find the slope? Theoretically, this is a good question. Theoretically, can we technically find the slope at 1 point? No. But the local linearity with limits show that we can make that denominator go to 0. You see what I'm saying? Of approaching that 1 point. Okay. Let's see. Let's go to this one right here. We're given, what form of the derivative right there? What form is that? Alternative. Okay. The alternative form is f of x minus f of c over x minus c. How many slopes does this find? 1. At what x value? 5. And only 5. Okay. So which of the following must, might, or never be true? The first one. Madeline, how do you read this? What is it asking for? What is it stating? What is it saying?
F of 5, like if you plug it in, you're going to get 3.
Okay, so this is saying not f of 5, but it's saying f prime at 5. Okay, so f prime, Madeline, what does f prime mean?
First. No.
Talk about the derivative. So the derivative at 5 is equal to 3. John, is that must, might, or never? must. Because look, this is the derivative equation. All of this is equal to f prime at 5. So if it's equal to f prime at 5 and all this equals 3, then it must be true that the derivative at 5 is 3. The steepness of the graph at 5, whatever the graph looks like, 1, 2, 3, 4, 5, let's say that the graph looks like this. We're saying that at 5 the steepness is 3. Up 3 over 1, up 3 over 1, up 3 over 1. Okay? Now, volunteer for B. Matthew, what does it mean? What is it asking for?
What it's asking is the derivative of 5 will equal 0.
Yeah, so the derivative at 5 is equal to 0. What is it?
Never.
Never. Not for this given information, because the derivative, everyone, is what? 3. That's saying that the derivative slope is 3. All of this is m, which is this. But it's saying m at x equals 5 is equal to 3. Okay? Alright, so now, what is this asking for that's different? Ellen, what is it saying?
It's asking for the location, like the point on the graph.
Perfect. It's asking for the location as far as what is the y value at what? At 5. Is the y value at 5 equal to 3? Evelyn, what would you say on this? It might be true. We don't know. Because if all this occurred at 1, 2, 3, and this was totally by luck, but right there, I did show a graph that the y value was 3, but it doesn't have to be there. I could still have this whole entire graph like shifted up 10 units. And the slope is still 3. So this is a what? Might. Okay, here we go. F is continuous at x is equal to 0. Any volunteers? It might be. We're not evaluating 0. What are we evaluating? 5. Okay? And what does continuous mean? You can draw without lifting up your pencil. And the 3 rules. It's defined as a point. A limit exists from both sidedness. And those equal each other. Otherwise, aka a defined point with local linearity. Okay? So how about E? Anybody? Must. Because if you're not continuous, then you have no chance of being differentiable. With me? You have to be defined. You have to be continuous first. And then at the very, very end, what is that one? I hear never, I hear must. Who said never?
I said never.
Okay, why do you say never?
Because if they're equal, then you get 0 on the top in the numerator.
Okay, so this right here on the left side.
Point, not the, you're right.
No worries, I want to talk about it because this is going to help you with your test that you have on Tuesday still. What rule is this right now, guys? The third rule of what? Of continuity, right? So the third rule of continuity says if the limit exists and is equal to that point, then it must be continuous. And this is the same as E. Would you agree? So with this being said, it has to be the same y value. So this anyone is a what? A must. Are we good? Okay. Let's go to I think we'll stop for that for as far as that is concerned.